your presentation.
Okay, can you see the slide?
Yes, but maybe speak a little bit louder, maybe.
Okay. Oh, so hello everyone. My name is Mohamed Khalil. I'm a PhD candidate at Polytechnic Montreal in the group of Professor Jamal Chowki and Professor Jean-Philippe Harvey. So my main project, actually, I'm working on recycling printed circuit board with the objective of producing value-added product and recovering base and precious metals. Today, I'm sharing some of the highlights of one of our recent articles that focused on the thermal degradation of West printed circuit board and some thermodynamics aspects. So electronic waste, like your old cell phone or your old computer, are everywhere now. The world generates over 50 million tons of every year of electronic waste, which is equivalent to 1,000 Titanics or even over 4,000 or 500 Eiffel Towers. So it's a large volume. In general, electronic waste, and more specifically the printed circuit board, are consisting of mainly metals, which is about 40% that include precious and base metals, and also organic parts, which is mainly epoxy materials or and polymers too, which represent 30%. These epoxies also are mixed with an organic material or a chemical substance called the flame retardants, and also a 30% of metal oxide, mainly it's alumina and silica. So in general, printed circuit boards are one of the most profitable material or type of ways that can be are interesting in an economic way or an economic perspective, since they include precious metals and more specifically gold. Compared to gold mines, printed circuit board can contain over 300 ppm of gold compared to 1 to 2 ppm of gold in gold mines. That's why it's profitable to focus on recycling electronic waste and more specifically printed circuit board. However, electronic waste also, and more specifically the printed circuit board, are mixed with chemical substance, as I mentioned earlier. It was called the flame retardant. Flame retardant, actually, it's a chemical substance with the aim of reducing or retarding or inhibit or reduce the flammability of electronic component, which is the plastics. And the problem here is when we try to get rid of our electronic waste by any thermal process like combustion, it generates toxic emissions. So one of these, like most known flame retardant types, are the brominated flame retardants, which represent 70% of the flame retardant that exists in the market now. And as I mentioned, the toxic emission released mainly coming from brominated flame retardant is the hydrogen bromide gas, which is a toxic gas when it's released. So in general, what we have now as a for recycling technique or process, starting from collecting electronic waste, dismantling and pre-processing, in order to recover these metals and recycle the electronic waste, we have whether the thermal treatment that can be at low temperature, high temperature. We can mention here smelters or the pyrometallurgical process. It includes also electrolysis and other process, and you can also mention the chemical treatment that can use hydrometallurgical process and bioleaching too, in order at the end to recover the metals or mainly the precious metals. So one of the most commercially or industrially used process, which is the smelters or the smelting. So a direct smelter actually of one printed circuit board is one of the most used process in the industry now, which is done in primary copper smelters in the aim always to recover the precious metal or the valuable metal. So it includes many advantages, including the generation of non-negligible amount of liquid copper matte, which is a perfect medium to promote chemical reaction. We also generate a slag phase that can remove oxide, which is like silica, which exists with very high concentration, over 30% of electronic board. And also we can recover the valuable metal like gold, silver, and platinum, palladium, using different process like electrorefining. However, one of the most of the challenge that exists with the smelters are the toxic emission released, as I mentioned, coming from plastics. Since plastic is one of the source of energy used in smelting process, so the breaking down the plastic by any thermal process generates these toxic emissions. However, the smelter use very high efficient scrubbing system to reduce this effect, the impact of these gases in the environment. So one of the other techniques that I'm proposing or using in my PhD actually is pyrolysis. So pyrolysis in general is a thermal degradation of organic material that can be polymers into a different product or value product like condensable gases or non-condensable gases and carbon black and carbon black. So using the same process for electronic waste has many advantages since it's a low temperature process. We avoid melting most of our metals compared to the smelters. We also have a challenge here, which is a generation of toxic emissions coming from the breaking down the plastics. However, in these conditions at low temperature, we can try or we can study how we can control these emissions. However, we also have a big challenge here, as you can see, when we try to simulate the process of the thermal degradation of metal circuit board using TGA or DSC, you can see different signals coming from this process, which is involved endothermic reactions, ectothermic reactions, maybe phase change too. So we have a big challenge here to understand fundamentally what is happening during this process. So in this study and on this article, actually, I'm highlighting part of it, which is related to understanding the process or the mechanism of reaction or the thermal degradation of printed circuit board. This is done by first using synthetic mixture between the flame retardants to understand how it interact or whether it interact with different components of electronic board. This include metals like copper, tin, and iron, metal oxide like calcium oxide, and also the organic part that include epoxy resins and polyethylene. Then we using the TGA DSC, we also simulate the pure substance that are composed of the metal bromide that might form coming from the reaction of the hydrogen bromide release and its interaction if it interact with the metals or the metal oxide. So we compare the synthetic mixture and the product of the synthetic mixture using TGA DSC and the brominated metal resulting to be able at the end to explain the thermal decomposition mechanism of the printed circuit board. So one of the examples that we can see here is using the thermodynamic simulation using FactStage to study the thermal stability of one of the bromide metals or brominated metal that can form, which is the copper 2 bromide. So as you can see here I'm presenting a thermodynamic simulation that deal with the thermal stability of one of the metallic bromides that may form, which is during the thermal degradation of tetrabromophenols A, which is copper 2 bromide. The idea here is that we are supposing that hydrogen bromide release is going to react with copper to produce copper bromide. So in FactSage, actually, the FactPS, or the for pure substance database, contains this thermodynamic description of almost 300 brominated compounds. And one of the important aspects to consider also is that the thermodynamic simulation of pyrolysis process using FactSage is very challenging since it's typically performed in an open reactor. So open reactors, that means that the evolved gas is constantly removed from the system, which impacts the overall composition of the system. So one of the approaches that we use to simulate this equilibrium or this system, sorry, is to equilibrate the condensed material with a given amount of inert gas that might be argon or nitrogen, and then remove the equilibrated gas phase from the system. So this type of calculation actually is performed using a mode called the open mode calculation. So as you can see, the simulation of copper bromide 2 or copper 2 bromide, 1 gram here is introduced to the system at 25 degrees and 1 atmosphere. The system is then heated to 1000 degrees. And according to this calculation, we can see that copper 2 bromide is firstly decomposed to copper 1 bromide. Then there is followed by reaction, the two different allotropic transformation. And then copper bromide start to melt and then evaporate. So this was done using FactSage. And then when we compare this behavior, and we're going to study experimentally, first the decomposition of tetrabromophenols A, as you can see in the first slide. Tetrabromophenols A, which is the flame retardant that we are discussing, starts to melt at lower temperature, which is about 180 degrees, and then start to evaporate at about 300 degrees. The evaporation of tetrabromophenols A release also the hydrogen bromide that we mentioned earlier. So the second graph actually shows the thermal degradation of copper bromide or copper 2 bromide that we just mentioned using FactSage that we simulated using FactSage. And now we are comparing what we simulated using FactSage in open system to our experimental test using TGA and DSC. And as you can see how they match or how the ability of FactSage to predict the thermal degradation of pure brominated metals, since we can see the decomposition of copper 2 bromide followed by two allotropic transformation, the melting and the evaporation of copper bromide. Then finally, in order to compare our signals that we have for a synthetic mixture of tetrabromophenols A with copper. We are comparing this to also to the behavior of the pure copper bromide and the pure flame retardant TBPA. So by comparing the third signals with the first two signals, you can see by mixing tetrabromophenol A with copper that the system actually starts always by melting the tetrabromophenol A, and then it's followed by an exothermic reaction between the hydrogen bromide released and the copper metals. Then it follows the same trend or the same behavior of the copper bromide, which is first two allotropic transformation, then melting copper bromide and the evaporation of copper bromide. So in this way, we were able to test the same composition or the same method. We applied it for different metals, as I mentioned earlier, different metal oxide, and also for the polymers. And we were able also to compare our result with FactSage and using DSC to confirm that FactSage, if it's able to predict what we can calculate or what we can analyze experimentally using DSC and TGA. So as you can summarize here, so to summarize this, as I mentioned, we started with pure substance like all the brominated metals, pure substance like epoxy resins also, and polyethylene, and also binary mixtures that compose from the flame retardant with all the pure metals, the epoxies and polyethylene metal oxide. We compare this using TGA and DSC and also FactStage. So from this study, we concluded that there is no interaction between the tetrabromophenols A epoxies and so any organic material, epoxies or polyethylene, there's no interaction, and also between the silica, 10 metals, they don't interact with the tetrabromophenols A. However, there is certain interaction between tetrabromophenols A and copper, iron, and also calcium oxide. They all share the same behavior, which is a exothermic reaction that take place when hydrogen bromide is released to the atmosphere. So here we can return again to our first graph that we presented for the thermal degradation of West printed circuit board. And by studying, as I said, individually the thermal decomposition of the different components, and with the synthetic mixture, we can summarize or we can explain the thermal degradation of West printed circuit board. As we can see, first it started with the polyethylene melting point at low temperature, followed by the melting point of the melting of tetrabromophenols A. Then there is two events that take place, which is the decomposition of the epoxy resins, which is the exothermic reaction. Also, there is an interaction or the reaction between hydrogen bromide with copper, iron, and we also, based on the concentration of copper, iron, and the calcium oxide, we can assume or we can predict that this reaction, if it takes place, it's going to take place between hydrogen bromide and mainly copper, followed by iron, considering their concentration, which is about 20% in copper and 10% in iron, while the calcium oxide is very low in concentration. Then it's followed by the evaporation of polyethylene, and there is two final small endothermic peak related to the copper bromide and iron bromide evaporation at higher temperature. So thank you so much for your attention, and if you have any questions, don't hesitate to contact me. Thank you.
Thank you, Mohamed, for this nice presentation. You were really on time. We don't have any time for questions. There are some questions in the chat, so you can answer them. And Mohamed, I'm looking forward for the PhD defense soon. So now that you've presented that, we're a few steps away from getting this PhD. So good work. So let's move on now to another topic. So we talked about